Oh, one last, we're going to get started soon, but I just want to mention one thing. The Adobe Connect chat room is no longer NYB-test. Now it's just NYB03 for you guys, okay? So I'll write that on the board. It's NYB03. And what's cool is that actually, if you're missing class for whatever reason, because I know some of you guys are away for sports or whatever, you can follow the class on this website, because you don't have to be on the school network to use it. Okay, so if you're late to class because you're stuck on the bus, or if you're at a sporting event, or just because you're sick and you just don't feel like coming to school that day, but you don't want to miss class, you go to c9.adobeconnect.com/NYB03. The O3 stands for your group. Alternatively, if you want to listen in on O2 and O1, you can do that as well. It doesn't bother me. You just need to know when they are, and then you can just chime in there. Okay. So I'm going to start that up, and then I'll get us started. I have some good news and bad news. Good news is that I got this to work finally. The bad news is I lost the audio recording of what we were doing just before. So those two problems. If you have issues with them and you need them to be re-explained, again, I have no issues. Just come and ask me. Okay? All right, so this is working. This is working. Screen is being recorded. Should be good. Perfect. All right, finally. All right, so today we're going to talk about electric fields and equipotential lines. What you have here, what does that look like? A map, exactly. What kind of map? There's a name for that kind of map. So, yeah, a topographic map, okay? So this kind of map you generally use to study la relief, like of an area, like which places are mountainous and which places are not. This is not that. This is an electric field map of an area, and that's because, not an electric field map, but an electropotential map. And you can see that different areas in a different place, because there's charges literally everywhere right now. Like all our computers and all the lights, every wire in the walls, every wire in the ground and the ceiling, even you guys produce electric fields, and the electric fields are going to produce what are called potential maps. And the potential map of this room might look like something like this. And it'll be denser, like for example here, it'll be denser around objects that are producing an electric field, okay? What are these like equipotential lines? I just have to review a little something first. First, I'm just going to draw your attention back to these electric field lines, like this and this. For a positive charge, it's going to be outwards. For a negative charge, it's going to be inwards. That won't affect our potential so much, because potential, as you'll learn it, is not a vector. Okay, potential is a scalar quantity, and it still can be positive or negative depending on what the difference of potential is. But it's a scalar quantity in the sense that it doesn't have a direction, and that's really, really important. So Martha, you can't see, right? I'm blocking you right. You okay? Okay. Let me know if you need help to find that thing. Another thing that we need to review is something else. When I say potential, what does that trigger in your mind? Things that you might have learned from the past. Yeah, Mark? Stored energy. Okay, so what was the term that you used for that? For stored energy, the official term for stored energy is potential energy. Exactly. So you guys have learned about potential energy last year in mechanics, and undoubtedly in high school as well. And essentially, potential energy is an energy that an object has the potential of becoming something else, right? So if I were to, what is this? Okay. Oh, you just kind of excuse it. Oh man, I'm weak. Ooh, that's my left hand. All right. Anyways, um, if I were to drop this, um, it has the potential of gaining a certain amount of kinetic energy. If I dropped it from higher, then it has a higher potential of gaining kinetic energy as it falls. Okay, so the same concept applies in electricity as well, except this time we're not dealing with gravity, we're dealing with electric forces, right? So if we have this here, for example, a positive charge, all right, and this positive charge is it going to attract or repel another positive charge? It's going to repel it, so maybe this is not a great example. Let's do a negative charge first. If this were a positive charge and I put a negative charge, so I'm going to change this to a negative charge, right? If I put a negative charge there, is it going to attract it or repel it? Going to attract it, similar to how this planet is attracting this object to fall downwards. This positive charge is going to attract this negative charge to fall downwards. And the further away this charge is, the more potential it has from gathering a velocity and coming closer to it. Okay, so if I were to write an object here, this is a very positively charged object, right? And I take an electron right there, all right? The potential is at a function of this height here, or this distance. We're going to call that distance r. Not height h, but distance r. Draw it. Exactly. Yeah, exactly. But we haven't, we're not going to really deal with that, but you're absolutely right. Yeah. So yeah, so this potential here is at a distance r is going to be proportional to what? How did we figure out what the potential energy was for gravity? How did we do that? Do you guys remember what the formula was? mgh, right? Now what is mg? What's the mg part? What? Which force? Force of gravity. All right, so it's a force of gravity multiplied by the distance that it's going to travel, right? So that. And what does force times distance equal to? Do you guys remember what that term was called? Work, exactly. So this is all work, and work is always force times distance. So far, so good. Any questions? I'm going to write this more formally down in the next slide. So if we were to make that comparison, we know that work, right here I wrote it down, work is equal to force times distance. Okay, at the top, force times distance. And if I move just, okay, sorry about. Unless you want to switch and sit next to Anne Michelle or something, or go one row back. Or just the table behind you is also empty. The force is equal to force times distance. We can make that correlation for with any force, right? The force of friction times the distance will give us the energy lost to friction. The force of gravity times the distance will give us the potential energy of gravity. Similarly, the force of the electrostatic force times the distance is also going to give us the work done by the electrostatic potential energy. So let's write that down. So force of gravity, or work, is equal to force of gravity times distance, or in this case, potential energy is equal to the force of gravity, which is mg times the height, right? And this gives us something in, what are the units of energy again? Joules, very good, right? These are square brackets. We have this now relationship that describes how you relate potential energy and force, and we can use that same exact relationship here. So the work of electricity, or electric potential force, we're going to call it that later, is equal to the electrostatic force times the distance x away from that object. Okay, so if I have a positive charge, big Q here, and some negative charge, little q here, what is the force equal to between these two? And they're separated by a distance r. How did we calculate the force? Well, I'm not asking if it's positive or negative. I'm asking what would be the function or the formula for that. That one? Absolutely. Q over r squared. Okay, do you remember this? Okay, good. And if this object, we're talking about the forces between this object, what is the height of this object if we're talking about potential energy? R. Okay, so then if I rewrote that, so it'd be, oh, come on. So the work is equal to K small q big Q over R squared multiplied by R, which gives us what? Exactly, so it'd be K Q small q big Q divided by R. Okay. So far, so good? And this is now what we're going to call a potential energy. Same kind of potential energy because it has the prospect of becoming kinetic energy or whatever. And it's measured in joules, similarly as the potential energy in gravity. The concept is exactly the same, essentially. Okay? And now, if I were to ask you a different question, is we measured force, right? And then we measured force on a specific test charge that we assumed to be 1 coulomb, and we called that electric field, right? If you remember, electric field is the force acting on a theoretical 1 coulomb object, or the force per coulomb. You guys remember the units were newtons per coulomb? So it'd be the force per charge, or that's how we kind of remembered it. There is a similar thing for potential energy in electricity. So if we took this potential energy, if we call the work per charge, right? Or in other words, KQ over Q over R, other words, PE over R, we end up with something KQ over Q. KQ over R over Q. And this is over Q. If we have this, if we do this to the equation to find out what the energy is per charge, what we end up with is KQ over R. And this here is something that you guys know inadvertently, which is voltage. Okay? So we have to find a definition of voltage. The voltage definition would be it's the amount of energy, potential energy that a charge can get per charge, if that makes any sense. All right? So we have some charged object that's big Q here, all right? And at any point, let's say I point to this object here, we can give it a potential. We call this potential, not potential energy. We call it potential because if I put a charge there that had a charge Q, I can find its potential energy. All right? Yeah, Sean. Yeah, sure. So the take-home message is potential, voltage, all right? Different from potential energy, joules. So potential is the amount of energy per charge that exists in an electric field. And it's in volts, exactly. So we have two new relationships that we can consider now. Okay, we have that electric potential energy is equal to KQ1 or Q1, Q2 over R. And we have that voltage, or just potential, is equal to KQ over R. Okay. That's confusing because now we have four formulas that look exactly the same. We have force, looks like KQ big Q over R squared, and we have electric field, which is K big Q over R squared. All right, do you guys see the parallel between these two and these two? Yes. No. All good? Wrong. So if you remember, electric field was equal to force per charge. So if I took force and divided by Q, then my Q gets removed. Yeah. So these four are going to be your main electrostatic formulas. It took us about 2 weeks to get here. 3 weeks. 3 weeks? Are we in the first week? Yeah, we're in the first week. It took us about let's say 2.5 to 3 weeks to get here. But these are going to be the basic and most important principles of this chapter. Okay. So here is that analogy again. If I have a small object versus a big object falling at a certain height, which one's going to have more potential energy? Can you guys determine that? Potential energy, not potential. The big one has more potential energy because the relationship is mgh. The greater the m, the greater the potential energy. And if I were to ask you what would be the potential at this point, then it would be mgh divided by m, which would just be gh. And that's the potential of any object of any mass being of that height would be proportional to the acceleration of gravity and the height at which you put it. And then afterwards, if we have the mass, then we can find out its potential energy. And that's similar to an electric field. So here I have a parallel plates, and a charge that's Q or a charge that's 2Q. One of them is going to have more potential energy, but they have the same potential. Okay, so the voltage of these two is going to be the same. So voltage of 1 and voltage of 2 compared to the potential energy of 1 and the potential energy of 2, we can say that V1 is equal to V2. But what's the relationship between potential energy 2 and potential energy 1? Which one's greater? PE1 or PE2 in this case? 1? What do you think, Marco? 2 is going to be greater because it's got a stronger charge. It's got 2Q charge. So P2 is going to have a stronger potential energy compared to PE1. Yeah. Is it voltage? Is it Q? Is it voltage divided by Q, or is it voltage times Q? If we go back, you got it? But that's a very important relationship that you just made. So Melanie wanted to relate how you can relate potential energy and voltage, and that's really useful because energy or potential energy, potential energy is equal to Q times V. Okay, that's an important thing to remember. You okay with that? So a little bit more about this. Now we're going to move into we're talking about potential energy now, but ultimately the important thing for electricity and magnetism and circuits and all that stuff is just voltage, right? Because we learn about batteries, we think about voltage sources and power supplies and things like that. So actually, the most important thing here is not so much the work or the potential energy as the potential itself. Right? This was my kind of like my segue. But just to finish off, this is a little summary of what we just talked about. Potential energy gets converted usually into kinetic energy. So did you guys ever see one of those water mills? Do you guys know what a water mill is? Yeah, so you have a wheel like that, and then you have water that flows downwards, and it hits the grooves in the wheel, causes the wheel to turn, and then the water falls back down. But then this wheel turning, it can be used for some kind of productive work. All right, now it's the same thing with potential energy in circuits is that you have a positive or a high potential area and a low potential area, and you have electrons that will flow in that direction, and that flow of the electrons in that direction will cause some useful work. Most of the time it's using a resistor or something like that. Okay? So we're slowly working our way towards non-static electricity. That's just a little preview. And we have to know that positive potential is going to be where the positive charges are. So here we're going to call this positive potential. Here we're going to call this, on this side, we're going to call this negative potential. And protons will go towards the negative potential, and while electrons will go towards a positive potential. Yep. Because think of it as, okay, think of it as gravity. All right, this is a good way to remember it. It's this positive charge is falling towards the ground, which is the negative charge because it's attracted by it. And so when an object, a gravitational object, is low to the ground, it's got low potential energy compared to if it were high up where it has high potential energy. Okay? Yep. Exactly. Yeah. It would be the opposite for an electron. Okay? In terms of energy. But what we label as potential is still positive and negative potential. The positives are always positive potential, the negatives are always negative potential. But an electron will have more potential energy closer to the low potential. Very confusing. I'm saying potential a lot. Okay? So again, more summary. So positive work increases the potential energy of an object, while negative potential decreases the energy of an object. That'll help us in terms of determining the sign of work if we ever need to determine that. So the example here is positive work is done to raise a book, right? So it takes, for me to lift this up into the air, it takes positive work to do that, right? Similarly, if I have strong positive charge here, and I take an electron and move it to here, am I doing positive work or negative work? Am I going against the force or am I going with the force? I'm going against the force, and then that would be the case of this one or this one. Yeah, so work in this case is going to be greater than 0. Think about which one makes you tired and call that one positive work. So picking up an object and bringing it up is more tiresome than taking an object up here and bringing it down. Going upstairs, dragging yourselves up those 5 flights of stairs or 4 flights to get to this class is harder to do than going downstairs. Going up is positive, going down is negative. So far, so good? So now we have to focus on drawing these potential lines. And this is where we're getting towards. And what's important is something called equipotential line. Right? So that means that, well, if I were to just break it down, what does equi mean? Equal, exactly. So equal potential line. So where is it around these objects? These are 2 examples. Where around these objects are the potential the same? And I'm just going to remind you that potential, now we're talking about potential, not potential energy, our potential is equal to kq over r. And at any distance r, the potential is going to be the same, right? Because the charge doesn't change. So if I were to say at this point here and this point here would have the same or different potentials? The same, because they're both at a distance r from a charge capital Q, right? So if you have to draw equipotential line that passes through these two, what would it look like? would be straight, sure, but then those aren't the only two that exist, right? It would be a circle, exactly. So like that would be what the equipotential line for a one charge would look like. Similarly, there is another equipotential line here, because they're all at the same distance r from the center, and there's another one here, and essentially they're everywhere. Right? Now this next one is a little bit more tricky, okay? Because as always, there's going to be an infinite number of equipotential lines, but we could kind of guess here. Okay, so now let's talk about just this positive charge. I mean, there is a negative charge, but it's quite far away. So right really close to that positive charge, you could basically, the electric potential felt by the other charge, right? So from this negative charge, is basically going to be zero close to this positive charge. So you can say that a positive charge far from another charge is still going to have its own equipotential line, so you can call it like that. You can make a circle around the plus sign. Similarly, for the negative charge, really close to it, the equipotential line is around it. But as you get closer and closer to another object, the equipotential lines will get affected by the next charge next to it. So the way you draw it is you have to draw your equipotential lines so that they are perpendicular to the electric field line. So equipotential lines must be perpendicular to electric field line. So if I were to draw a perpendicular line here, right, just in the middle here, and I had to continue it, how is it going to intersect all those other equipotential lines in order for it to be perpendicular to all of those electric field lines? What would it look like? So I have a line here, and at some point it's going to intersect this next one here, this one below it, and it has to be perpendicular. So if it has to be perpendicular to all of these lines, then what is it going to look like? Yeah, it'll be a straight line like that, where it's perpendicular to all of them. What about just a little bit to the right of this straight line? If it's going to be perpendicular to here, then and it has to be perpendicular, and it's got to be a little bit more angled for this one, a little bit more angled for this one, a little bit more angled for this one. So it's going to end up being something like this. And continue doing that for all of them, and you'll see that you'll end up with something like this, hopefully. Oh no, I'll redraw it. Something like that. Okay. And if you add many charges, you can see how this can become like a topographical map, right? And these are two very simple situations because I'm dealing with 2-point charges. They get a bit more complicated when you have linear objects and things like that. So here it is, a summary of what we just said. The electric field lines and equipotential lines are two equal and opposite charges. The equipotential lines can be drawn by making right. So that's the really the important part for the electric field line. We can calculate the potential at any point, right? So if I had a point here, if I had a point right there, and I ask you to find the potential at that point, well, it's easy. You just sum up all the different potentials. So you have this distance, we're going to call that r. We're going to call this distance, we're going to call that R1 and R2. You can find the potential at that spot by doing K, and we're going to close on Q1. This is Q2. It's going to be KQ1 over R1 plus KQ2 over R2. And it's going to be negative on this one because it's a negative charge. Okay? And it's a scalar quantity, which means that I don't have to determine where it is in relation to that. It's not a vector, so it's not like I have to draw an arrow to find specific angles and all that stuff. It really is just the distance to those charges. I'm going to call this the voltage or the potential at point P. I can find that using this relationship like that. Okay? So your next lab is basically this. Okay, you have to, you're going to be given two charges on opposite sides of a piece of paper. They're not going to be necessarily point charges. Some of them will be more complicated shapes. And you have to use a voltmeter to determine the equipotential line. So if you take a voltmeter and you put one probe of that voltmeter here and one probe of that voltmeter here, what should your voltmeter read? If they're equipotential, what is going to be the difference in potential or the voltage of those 2 points? Shining? Zero, exactly. All right, so you're going to find these equipotential lines. It's going to be trial and error, and you're going to be able to draw your equipotential lines. But the purpose of that is to, once you have the equipotential lines, you can work your way this way to get to the electric field lines. And the purpose of the next lab, is to draw those electric field lines using equipotential lines. So you have a voltmeter, you're going to be testing different spots. There's a lot of trial and error, and you can find out what the electric object. Similarly, if I took one probe, so you know how voltmeters work, it's got two prongs, right? If I took one prong of those voltmeter and put one there, and put the other one, so I put one prong there, one prong here, it's going to read what? What is it going to read on my voltmeter? According to this drawing here. 15? How did you get 15? By adding those two, okay, I understand how you got that. But is the voltage at a further point going to be higher or lower than a voltage to a closer point in this case, which is negative 10? It's going to be, it should, because it's further away, it should be less, right? Or absolute value less. So it's going to be 5 because everything along this line compared to this point, which, because that point is going to be 0, it's going to be negative 5 volts. Okay, so you can, on your lab next week, so this is just some advice, you can put one point of your electrode at the center of where the source is, and then poke the other end at different places, try to find places where the voltage is going to be the same. And that'll help you determine the electric potential, equipotential line. Okay, that makes sense? So now if I'm working from here and going to this direction, then I have to draw my electric field lines so that they're perpendicular to the equipotential line. So for example, one will be this way, this one will be this way, but once you get here, they're going to have to look like that, right? Well, it's negative, so the arrow should be downwards. Okay, something like that. All right, so that's basically what your lab is. You'll see the trial and error nature of the thing. So here are the definitions. We talked about all this. Definition with a constant potential. So everywhere along an equipotential line, the voltage is the same. That's what that's saying. And for a point charge, you're going to see a diagram here. For a point charge here, in the middle, there is equipotential surface and a sphere all around it at any radius r. Okay. So there, those would be all equipotential, and everywhere along the sphere as well. Yep. This one? Not in the circle, but on that circle, on the line of that circle. Inside of it, so if you had a charge, like where I put my red dot here, then inside of it, then there would be another equipotential line along that circle. Okay. And everywhere on that new circle I just drew, that would have. So far, so good. For parallel plates, the equipotential lines are just plates, right, or surfaces in between those two plates, similar to what I have here. So, for example, there's going to be electric fields that go in this direction, and the only thing perpendicular to that at all points would be another surface, basically parallel to one of those plates of the parallel plate. So, if I had two parallel plates, kind of like what we did in the last class, assuming those are parallel plates. If I have a line here, then the voltage is the same everywhere along that line in between the two plates. So that would be an equipotential line. What I want you guys to do now is you can't draw on your screen. How many of you have touch screens that you can draw on? Okay, decent amount of you. Okay, I mean, try as best as you can to do this problem. Those of you who have a touch screen, try to do it on your screen. I want you guys to draw the equipotential line. Sorry, these are the equipotential lines. Draw the field lines of these diagrams. If not, try to reproduce it on your book, in your notebook, and try to draw them to make it so that every time you draw an electric field line, it comes out to be perpendicular to the potential line. Yep. Or just draw as many as you can. You can do them for points A, B, C if that helps you to start off with. But essentially, what you do is you do it for every point. Yeah. Right. But it has to pass, so the electric field line will pass through all of the potential lines. So if you have a field line that passes there, that is you should pass all of these lines. So basically, I have like one line to draw from this point and going there. Right? That's try and make perpendicular to each one of these. Each one of these. I see. So I only draw one line. So at a certain point, the electric field can only be in one direction. Yeah. Because we can have cross. Yes. One line. And then I don't know how, but it's gonna have yes. Yeah. Yeah. You drew inwards. I want to see why. Correct. So you don't want to the lines on the point towards positive. But I like how you do the arrows. Which app are you using to draw? Okay. So Bronwyn had the great idea to drawing the lines, and she had the right to do that because we're talking about electric field lines, and electric field lines have arrows. Trying to figure out which direction those electric field lines are going. Drawing, like giving an arrow. Yeah. Usually I have something that kind of looks like this. It's not like an exact science or anything like that, and I don't expect it to be on your lab. As long as the information you have doesn't contradict what you drew, that's all that matters for me. Yeah? Is that what you guys got? Somewhat. So, if I were to characterize this by saying where are there really strong charges, where would you say? Like off this map, where could you put charges to make this make sense, kind of? And we'll talk about just point charges because we'll try our best. Mark? Around point C over here? Okay, what kind of charge would there be? Yeah, negative. Where else? Yeah. Top left corner, so over here. Okay, what kind of charge would there be there? Also negative. And then what kind of charge would be there? Something like that. We are good with that? That one? No, because there's going to be an infinite number of equipotential lines. So if I have a charge, like a point charge there is literally a million. I mean, it's an indefinite number of equipotential lines surrounding it. what makes it so that I think that there's a charge there, or that way Mark thought there was a charge there, was because there's so many lines pointing in that direction, so many electric field lines pointing in that direction. Okay. Any questions about that? Okay, let's solve this problem together. A proton is released from rest at point Q, where the potential is 0. Afterwards, the proton, and then tell me what the proton does. Does the proton go to the left or the right, etc.? Read the options. Give me an answer. What do you think? Moves towards, so a proton moves towards P at a steady speed. Bronwyn, what do you think? Moves towards P at an increasing speed. Nicholas, you agree with that? Okay. So Marco said steady speed. Bronwyn says increasing speed. They're right in the sense that it goes towards point P, but which one of them is right in terms of the speed? Is it constant or is it non-constant, and why? Think of potential energy. Yeah. Exactly. So it has to be an acceleration. It has to increase speed. It's kind of like an object falling. So the acceleration is increasing. So the answer would be C, moves towards P with an increasing speed. All right. So here's another one to think about. Rank in order from largest to smallest the potential differences. So now we're looking at delta V between V12, V13, and V23 on these points. So which one has the highest potential difference? What do you think? So delta. So if they're equal, what is going to be their delta V? Their delta V is going to be the same. How does that work? And the delta V. So if I did V1 minus V2, what would be the delta there? It would be 0. Okay. Delta V13. So it's going to be, first of all, is it going to be positive or negative? So we say V13 is the same as saying V3 minus V1. It's going to be positive. What's the highest potential? Close to Q or far from Q? That's the lowest or highest potential? Highest. I'm just going to remind you that voltage is equal to KQ over R. So that the higher the R, the lower the voltage. So in this case, it would be negative. So, okay, so in this case, it's going to be less than 0. Now, what can you say about V23? Same thing. But what can you compare? How could you compare these two now? Think of them in terms of R. Because you said that the potential between 1 and 2 is the same. So the difference between 1 and 2 together with 3 should also be the same, right? I would say that V13, delta V13 be equal to delta V23. And they're both negative. So if we're saying from largest to smallest, it would be delta V12 is greater than delta V13, which is equal to delta V23. Now, no, I mean we're not talking, because it's voltage, there is no other charge. The only charge that we take into account is this one at the center, and it's a proton. And so therefore, close to it, it's going to have a really high potential, and far away from it, it's going to have a really low potential. If it was an electron, it would be the other way around. But in this case, it's a proton. Yeah, and say that again. The electron in the middle would be that very close to it. If we look at it, it's going to be K or negative KQ over R because it's an electron. And R is going to be really high, so it's going to be a really negative. So it's going to be, how do I draw really negative? It's going to be very negative because it's close to it and it's a negative charge. So R is going to be low. Yeah. If you really, exactly. Okay. Let's do an example. You guys, okay, we'll do one. How many examples do we have here? 2 examples. Okay, let's do 2 examples and we'll call it a day. So a proton is traveling at 800,000 meters per second from infinity and brought to a rest on an electric field. Did the proton move into a region of higher potential or to a region of lower potential? First of all, can you answer that for me? Let me just draw it out here. There was a proton that was moving and it eventually stopped here. So was this low potential or high potential? Okay, how did you determine that? But if there was a negative charge here, which is what you're saying by telling me that it's low potential, would it stop at all? Well, it's negative. So Marco is saying that that's a negative charge. So are you disagreeing and saying that that should be a positive charge? Aha. Let's say you threw a ball against the wind. All right. Eventually, it's gonna stop and maybe come backwards. Let's say if the wind is really strong. All right. But if the wind was behind you and pushing you that way, then your ball would actually never stop until obviously it's the ground. But that's different. That's a different situation. So in this case, if there is something that's stopping it, that means there's a force opposing it, causing it to decelerate and causing it to come to a velocity of 0. So if that were the case, the force is in which direction? And this in my drawing, is it upwards or downwards? The force, not the initial velocity, the force. Upward, right? So if the force is upwards, then that means that it has to repel my proton. So what repels a proton? Another positive charge. So this has to be positive. And so is it going to an area of high potential or an area of low potential? High potential. No, because if it's getting attracted all the way from infinity, then why would it stop at a certain point and not just drag it all the way in? That would make it draw it in even faster. Yeah. So it's a high charge. And now I'm asking you, what is the delta V between at that point? What is the voltage at that point? So we need to come up with Melanie. Was it Melanie? I think you came up with that relationship that you said that energy or potential energy is equal to QV. So I can say that the change in potential energy the same as Q and the change of voltage. Is the potential, you guys said that the potential is increasing. I definitely agree with that. Where is that potential energy coming from? Something is causing it to have a potential energy. Where is that potential energy coming from? Remember the law of conservation of energy? The only physics law that you can never break, unless you're talking about quantum mechanics. But energy is always conserved. Yeah? Yeah, absolutely. The kinetic energy is getting lost and getting converted into potential energy. So the change in potential energy is the same as the change in opposite direction of the change of kinetic energy, right? So if we had a kinetic energy of 1/2 mv squared because of its velocity, and at the end there was no kinetic energy, then all that kinetic energy was theoretically converted to potential energy. Okay, and then you just have to divide that by Q in order to get your change in voltage. So the change in potential energy is equal to the change in kinetic energy. And because it's a proton, we know that mass is 1.67 times 10 to the negative 7 kilograms. Say that again. Okay, 5.34 times 10 to the 16 joules. That was the potential difference, the potential energy difference. And if I were to divide that by Q, so potential energy divided by Q gives me my delta V. It's what? Minus 16? Well, you had a positive number and you divided it by a positive number. It should give you a positive number. Oh, okay. So say that again. Oh, minus 16 here, okay. And then for the charge, yep. Okay, so let me restart. You understand this relationship here? Okay. So we have to find out the change in potential energy. If we find the change in potential energy and divide it by the charge, I'm going to get my voltage, which is what the question is asking for. Okay. So my change in potential energy is going to be equal to my change in kinetic energy. Correct? And my kinetic energy, well, it had an initial velocity of 1/2 v initial squared, and it became some other energy, which was 1/2 v final squared. And this value is just 0. So my kinetic energy that I had at the beginning from going at this velocity is going to be converted to potential energy. And taking that potential energy and dividing it by Q is going to give me my voltage. If you guys have an answer, I'll take it. 3.34 times 10 to the 3 volts. Are you guys in agreement with that? Can you guys confirm? Yeah. Sorry? Yeah, use the mass of a proton. Exactly. I did it initial minus final because it's the opposite of potential energy. So it'd be negative final minus initial, or initial minus final. Delta KE equals to negative delta P. So I did it the opposite. And in any case, are you going from an area of low potential to high potential? Or are you going from an area of high potential to low potential? So down here, what kind of potential is it? all the way up into at infinity. We said here it was, here we gave an answer already. We said here was high, so this was low. So this is your Mark. Mark, you have an answer? You have a question?
Formula for final velocities, you get an answer.
Yeah.
And then what do you do after that? You like divide that.
But what is its final velocity? It says in the question actually.
It's 0, yeah, but for the initial velocity. So after the initial velocity.
Yeah.
And then what do you do after that? After you get like kinetic energy from the initial velocity, what do you do?
Okay, so you need to physically, this is what's happening in your mind. So in physics, that kinetic energy is getting converted to potential energy. So all that kinetic energy it had from the start, from that 800,000 meters per second, that kinetic energy is getting converted to potential energy. All right, and now I have the potential energy, and for voltage, it's potential energy per charge, right? So I divided by charge to get the voltage. That's which is what the question is. Yeah, that gives you the voltage. And I was saying before, if this here is the very high potential, then this must be a very negative potential at the very top, and your change in potential is increasing, so your delta V should be a positive number. And that makes sense. So delta V is a positive number. 3.34 times 10 to the 3 volts. Is that what you got? It was the kinetic energy, which was 1/2 mv squared, divided by the charge, which was 1.6 times 10 to the negative 19. I'll stop here. The take-home message in this case is really just potential energy per charge gives you voltage. If I had to summarize that into one sentence, potential energy per charge gives you voltage. Know how to draw the equipotential lines and the electric field lines for the lab. The two problems we did at the beginning of class, those will be representative on what's going to be on the quiz. Essentially, next class is going to be we do a quiz and then you do the lab for the rest of the period. Okay? Okay. See you guys. Have a great day.
Yeah. Ways to find the
So say that again. We're talking about this?
Yeah, it's basically electric fields or stuff.
Yeah.
So are we going to be using those for basic formulas the whole semester?
No, not the whole semester. For this first 1/3 of the class. Yeah. What's that? Yep. Let me just pause it.